So let's begin with the question, what is visual search? Let's imagine that you want to buy a dress on Allegro, but you only have its picture. For example, a friend asked you, buy me this dress, and because I don't have an account on Allegro, and could you help me? So I would like to answer, just sign up, it's easy, but in the end, I'm trying to help and trying to find this dress on Allegro. Of course, I could use normal text search and just type a phrase, red dress, because honestly, I cannot say much more about this dress and get some results. We could also use attribute filtering. We will choose a red color, long sleeves, and no pattern. And I think that actually we have this dress on our results, but I'm not sure. But what about such dress? What colors should we choose here? Blue or white? Sleeves long, okay, but what pattern? Chinese porcelain? There is no such pattern on Allegro filters. But we have a picture. So a picture, of course, consists of pixels. Pixels are 3 RGB values. And we can represent this picture as a matrix or actually a tensor. We have a simplified diagram of such representation on the right for one channel. And we can use this representation to search for similar images. That is, images that have similar representation, that are close to our query, according to some distance, for example, Euclidean distance. So the first image is the query. Next, we have 5 most similar images. And actually, with pixels, we can find dresses that have one thing in common. They all lie on the dull floor.
Okay, so since pixels are not enough and we are on a ML conference, the obvious answer is let's use neural networks. And in this case, we'll use a ResNet model, which was originally designed for classification. But we'll be using the representation it produces on the penultimate layer, as highlighted on the slide. Obviously, we have to pre-train this network on something. As we all know, transfer learning works, and quite well, actually. So we'll use the classic, and we'll start with ImageNet, dataset originally designed with 1,000 classes, starting with dogs and cats, ending on trucks and airplanes. It may not be the perfect setup if you want to find a similar dress, but let's use those representations and see what happens. So we have the same query with Chinese porcelain dress, and we've got 5 results, and honestly, I have no idea if that's better or not. We got rid of the floor, but it's actually hard to say if we have made any progress. So let's settle for a way to measure our effectiveness. We'll pick accuracy at 5 as a percentage of successful queries, where by a successful query I mean one when we get the item within 5 most similar images, and obviously a failed one where we don't. So we tried a pixel-based approach, we try now an ImageNet-based approach. Let's see what are the results. Well, the pixels gave us 100%. The ImageNet is 200 times better and achieves whopping 2%. Well, maybe let's try something different. Let's make use of something that we have on Allegro already. We could turn to attributes and train our network to predict their values. Basically, each offer on Allegro has some attributes. The seller provides those values. We can predict them and take the representation. Also, we have over 700,000 offers just in the dresses category, so amount of data is not a problem. Let's use that and see where can we get.
Okay, so we can measure how good are our attribute value predictions. And here we have, with any sensible metric, and here we have chosen area under the rock curve. And what we see here is that after an initial drop here caused by unfreezing of the backbone for fine-tuning, our results became very good very quickly. I would like to say that they are suspiciously good. Because we have a 97% accuracy on attribute prediction. And probably we have a problem here. And the problem is that our dataset contains many duplicated images. And what's worse, these duplicated images are not exact duplicate. There is a little difference between images. You can see it on the right. And having such duplicated images in dataset leads to a significant problem. I mean data leakage between training and test datasets. So how can we mitigate this problem? Of course, with some kind of deduplication. And our deduplication pipeline consists of several steps. First, we auto-crop all images to get rid of some random translations. Then we compute a perceptual hash, actually a variant based on discrete cosine transform. We also add some additional information about hue because this implementation of perceptual hash is color invariant and color is interesting for us. And with such hashes we can perform the duplication, and we also can count how many duplicates we had. And it actually turns out that we have had a lot of duplicates. And after the duplication, our dataset becomes suddenly much smaller. But this is not the end of our problems. Now, these duplicated images have different attribute values because they came from different offers. And so we have a noise in our attributes. And we must employ some means to denoise them. And we do this here by majority voting. Okay, we also apply some data augmentation to our images, some random crops, random rotations, to make our dataset more difficult and more diverse. Okay, so let's see. It turns out that our model based on attribute predictions produces quite good results. We have 43% accuracy. Unfortunately, the actual search results are not very impressive. While we managed to deal pretty well with overall cut of the dress and, for example, length of the sleeves, we certainly have problem with color here. And similar here, we have found some dresses with checkered pattern, but this pattern is obviously different than in the query. And for the dress in the Chinese porcelain pattern, we have 4 random dresses with just different pattern, and surprisingly 1 exact match, the second one. Okay, so, but the real problem is that while for the dresses category, we have a lot of attributes to predict, it's not the case for many other categories in Allegro. And either we don't have any attributes there, or the attributes that we have are not appropriate to visual prediction. And the second problem is that we are not really controlling what we are learning. Our model is trained for classification, so for attribute prediction, but during inference, we use it for completely different purpose, image retrieval.
Okay. Excuse me, and how do you use attributes? Because before, with ResNet, you could just, I don't know, take some embedding, and for these attributes, do you also take some embedding?
Yeah, we take the embedding from the same layer, but instead of classifying onto the original categories from the ImageNet, we are classifying.
There are many classifiers for different attributes, yeah? Okay.
So now in machine learning, we have a question, what to do next, and we can either start with better data or a better model. So let's start with better, I'm sorry, I lost it. So as long as we cannot use attribute prediction for all categories, maybe we can do something else. We'll borrow the idea from the previous talk from Kalina and Piotr, and we'll start with Siamese networks. So just a quick recap. We start not with a single image, but with a pair of images. Then we pass them through our encoder. We get the embedding for the first image, for the second image, and we want to predict if that's the same item on the images, that would be the positive, or not, a negative. We'll call the former a positive pair and the latter a negative pair. So now here comes the question. How do we obtain those image pairs? For the negatives, it's quite easy because you basically take two random pictures and you get, with high probability, a negative. But what about positives? It's much harder. We could turn to external data sets like Stanford Online Products dataset with over 120,000 products crawled from eBay. But unfortunately, there are no fashion photos, and we have to deal with fashion first. So there are other data sets like Deep Fashion, where we have nearly 1 million images of clothes. That would be perfect. There are also some smaller data sets like Fashion AI or Fashion IQ. And while those data sets would be perfect, they all have one thing in common. They cannot be used commercially.
Okay, so since we cannot use these external data sets, maybe we have some internal ones. Let's look. On Allegro, we have such cool feature as product reviews. And our users also like them and write them pretty often. And they also sometimes upload images of the products they bought. So we could build a great data set of pairs based on these images. And such a data set, such pairs, would have this advantage that one of the photos come from our offers. So this is high quality photos on white background. And the other photo comes from our users. So it's probably poor quality and it's very similar to the photos they will use later in image search. Of course, not all pairs are perfect. There are some problems, but the real problem is that while for the whole Allegro we could build a data set of more than 40,000 pairs, for fashion category it would be 1,500, but for the dresses category our data set would consist only of 27 pairs. So, as you know, neural networks need a lot of data to train, and 27 is certainly not a lot. But we have a lot of offers on Allegro, and almost every offer have several photos of the same product. So we could choose random 2 photos from every offer and build a data set based on these pairs and try to train a model on this. So with this approach, the numbers are much better. For dresses category, we can build a data set consisting of 1,500,000 pairs. Okay, so hard to call it a success. We achieved a whopping 6%. We are better than a network trained on planes and birds. But we are far below the results of the model trained on attributes.
So it's now for the moment for the question, better data or better model. So we'll start with better data, as we believe good data is crucial. So let's take a look at our data set, and we can immediately see that some of the images of the dresses are, well, not dresses. Basically, you've got some size tables, directions to shops, logos, and so on. And while those may be useful for the buyer, they are completely useless and confusing for our model. What's worse, we get some very easy, naive image pairs, where we get mirrored images, crops, even duplicates. And that's, while we can deal with that to some extent while we are training our network, it leads to a much bigger problem, because our model learns a very shallow relationship between the images and eventually degenerates just to pixel similarity, which didn't work. What can we do? We could try to somehow clean our data set and we can find 8 distinct categories within our images. There are 4 of them are quite useful for us. The first 2 are on a white or a solid background, which are more shop images. And we have the product on their own or a model wearing the product. Then we have the same products, but in more natural environment on much uglier background. Again, either the product or a model wearing the product. And those images, the latter, would be much closer to what the user will use later in their search. We also have some, well, less useful images. We have collages of multiple images, which are widely popular in the fashion category. And while they do look nice, because they show you a combination of few variants of the item, it's quite hard to assign a proper label from the first 4. Then we've got close-ups and details, and I cannot believe that the model would be able to predict a dress based on one button. Also, we've got those size charts that end up in the trash category, and the mandatory other category where all the rest goes. Okay, we have 8 types of images, but how can we use it to our advantage? We could basically train another model that would classify those types, and then use it to clean our entire data set. But then again, to train a model, we need some annotated data, and there is no way around it. Or is it? We could refer to something called active learning, where we basically take a few hundred examples, we annotate them by hand, then we train the classifier based on that, we make predictions, then we keep those with high probabilities values, and then we simply correct some of those which were where the model was not certain which label to assign. This way we repeat this process a few times, and within a dozen or so hours we ended up with 20,000 images and model that was quite sure which label to assign with accuracy over 98%. Okay, so let's use this model to create our data set. So we'll take all the images, we'll pass them through our encoder, we'll get one of the 8 categories, then we'll discard the junk categories with collages and so on, and from the other ones we'll create pairs that always differ on the product, model, and nice or ugly background dimensions, so that our model in the end would hopefully learn the similarity between the item itself and not the background, what's around it. This way, however, we get much smaller data set. From starting 1.5 million items, we get only 12,000 pairs after filtering and matching, so that's way worse. But fortunately, here size doesn't matter, and we get much better result. We get 21% on filtered pairs compared to the 6% that we had previously. Okay, but it's still worse than 33% on attributes.
Okay. So now we have already better data, so let's try to use a better model now. So this time instead of pairs, we will analyze triplets of images. We will call the first one a query or an anchor, as in previous presentation. The second one will be a positive, and the third one will be a negative. So very similar as in previous approach, only there we had 2 pairs, query negative and query positive, and now we have one triplet. And the idea is to make the distance between query and negative larger than the distance between query and positive image. And what's more, we would like that this query negative distance was not only larger than query positive distance, but larger by some margin, m. Okay, so let's formalize it. So we want to minimize query positive distance, maximize query negative distance, but if the difference between distances is already big enough, then we don't want to push the negative any further away. We don't want to make it too far. Okay, So this is our loss function. This is this triplet loss function. Okay, and finally it worked. A model based on triplet loss is better than a model based on attribute prediction, and we have 50% accuracy. But we still have some time, and we can work on our model. So here I would like to focus on a certain fact that when our negative is already far enough, we don't want to push it further away. But when we choose our negatives at random, and we do here, then it quickly turns out that most of the negatives are already far enough. And then the loss function indicates that the loss is 0, and there is nothing to do, and as there is nothing to do, our model learns nothing new. So to make it learn, every time we are producing a triplet, we are trying to find such a negative that is close to query, within a margin or even closer. And in this way, the loss function is positive and our model can learn. Of course, it's not always possible to find such negatives, but we try to find them. Okay, so let's look at the chart showing how the percentage of active triplets, so these triplets that have positive loss function decreases as training progresses. So for random negatives, we start with 80%, and it quickly drops to about 10%. So during the most of the time of the training, we are only learning from every 10th example. And with hard negatives, there is also a drop in this active triplets active triplets percentage, but even late in the training, we have half of examples still usable for training. And it also has a significant impact on our accuracy. With hard negatives, we have 71%, and it's much better. Okay. So, we have come a long way, so let's compare the results of our models based on attribute prediction on top and on triplet loss with hard negatives on bottom. So it's immediately obvious that we are dealing now much better with color. Also, there is no bias associated with nice or ugly background and with the presence of the model on the photo. But the model is not perfect. The model based on attributes deals pretty well with the overall cut of the dress, and model based on triplet loss have problems. In the results we have dresses without sleeves or with other cut than the dress in the query. Similar here. We have found some dresses with similar checkered pattern in similar color, but also here we have in results dresses with long sleeves, and in query the dress was with short sleeves. And for the image of the dress in Chinese porcelain pattern, we actually have 3 exact matches and 2 dresses with quite similar pattern, but again with different cut. So as you see, we have some problem with coherence of attributes here. So are you thinking what I'm thinking?
Well, I have no idea what you're thinking, but I think that I know what Jarek is onto here. So what would happen if we were to combine those 2 approaches? Here we have to mention that we said previously that it's quite hard to use the attributes in every category, but actually for the fashion department, for majority of them we do have the attributes and we can use them. So let's put that problem aside for a moment and see what happens. Here we'll begin with our triplet. we'll pass it through our encoder network, still the same ResNet. We'll get some embeddings, we'll calculate our triplet loss on that, and then we'll add a classification head for attribute prediction. So this way, our results should be better. But here comes the question, which one is more important, triplet loss or attribute prediction? It would be hard to guess which one is actually more important, but we can fortunately let our model decide by using a technique introduced by Alex Kendall for multitask learning, which basically adds a parameter for each loss term and allows the model to learn it along the way with the network weights. Therefore, we do not have to worry about that. So, we had a great idea, at least I think it was a great idea, some techniques to deploy it, and well, not everything in deep learning works as expected, and so logically, and in the end, we get a bit worse model.
Okay, but look again at our model. What can be a problem here? So, what we did, and we didn't mention earlier, is a L2 normalization of our embeddings before triplet loss. And while this normalization works pretty well with triplet loss, it turns out that it's not appropriate for classification, so for attribute prediction. So we have introduced a small change to our model, and we changed the input of our attribute prediction head to unnormalized embeddings. And this small change also led to a small increase in accuracy, and now this model based on these two approaches, attribute prediction and triplet loss, is slightly better than the previous one.
Okay, so what else can we do? We can take a look back at our journey, and we'll see that we are still using the same ResNet backbone, pre-trained on cats and planes. We still don't sell those on Allegro, at least not in the fashion department. Also, we have high-quality data sets, but they are quite small. So what can we do? According to a recent, well not so recent, previous year paper from Facebook, pre-training on large data set works. They tried it on Instagram. It worked well. We cannot use their data set because it's not available, and the model is, as you can guess, not available for commercial purposes, but we can borrow the same idea and try it on our data. So we'll go back to our random pairs approach and modify it a bit. So we'll take the first image from author as our query, then we'll take a second image as our positive, no matter how it looks like. Then in our training, we'll take from our batch the hardest possible negative. This way we are using all available offers, meaning we get a data set with over 100 million images, and we called it random hard triplets, which made sense at the time. So, did it work? If you recall, on ImageNet we got 2% accuracy. Then with random pairs on Siamese network, we obtained 6%. Now, after training on the whole Allegro with huge data set, we get 37%, which is a quite a substantial improvement. So let's see if actually using this pre-trained ResNet and combining it with our two-in-one approach would help us. Well, it did. We get 81% of accuracy with the pre-trained two-in-one approach, and that's quite a good value. But as you saw previously, with our attributes-based prediction, good accuracy not always comes with great results. So let's see for ourselves if this actually worked as we expected. That's the original query. We've got 5 dresses, all of them with long sleeves, pretty similar neckline, and they are all red-ish. So it looks good to me. But here comes another question. What happens if you don't have a picture of what you are going to buy? I mean, you have some vague representation, what you would like. You have no idea how to type this down. So let me ask you this. Can you draw? If you can, you could try to draw something. And, well, it turns out that it works. We had no idea if that New Balance shoe actually existed. And, well, something very similar did. but well, not of us can draw well, nicely, but maybe some doodling would be enough. Yes, it is. So we can say that our model generalizes quite well, and
Okay, so thank you for your attention. If you have any questions, this is the best time to ask. We will be glad to answer.